Hello, it's me, Oscar from Marijuana Garden.
Imagine a world where empty space isn't actually empty. What if, instead of nothingness, a hidden sea of energy churns beneath the surface, brimming with potential? This isn't science fiction, this is the strange world of quantum mechanics. And in this world, even the vacuum can dance. This dance, my friends, is what we call the Dynamic Casimir Effect. The Dynamic Casimir Effect is a mind-boggling phenomenon where we can essentially trick the universe into creating something from, well, nothing. It's a testament to the bizarre yet beautiful rules that govern the quantum realm. To understand this dance, we first need to grasp a fundamental concept, the static Casimir effect. Imagine two mirrors facing each other in the vacuum of space. You might think there's nothing between them, but quantum mechanics tells us otherwise. The vacuum is actually teeming with virtual particles, constantly popping in and out of existence. These fleeting particles create waves, much like ripples on a pond. These waves exist both inside and outside the mirrors. However, the space between the mirrors is so small that only waves of specific wavelengths can fit. This creates an imbalance in the pressure exerted by the virtual particles, pushing the mirrors together. This force, observed in experiments, confirms the existence of this quantum sea of energy. Now let's shake things up, literally. Imagine vibrating one of those mirrors rapidly. This rapid movement disrupts the delicate balance of virtual particles in the vacuum. As the mirror jiggles, it essentially imparts energy to the virtual photons, giving them enough of a boost to become real detectable photons. This, in essence, is the Dynamic Casimir Effect. By rapidly changing the boundary conditions of the vacuum, we can coax real particles into existence. It's like shaking an apple tree and watching as ripe fruit falls to the ground. Except in this case, the tree is empty space and the fruit is light itself. Section 4. Catching the elusive light. For years, the Dynamic Casimir Effect remained a theoretical curiosity. Then, in 2011, a team of physicists managed to observe it directly. They used a superconducting quantum interference device, or SQUID, a highly sensitive magnetometer, to detect the faint microwave photons generated by a rapidly vibrating mirror. This groundbreaking experiment not only confirmed the predictions of quantum theory, but also opened up new avenues for exploring the strange world of the quantum vacuum. Section 5. The future of nothingness. The Dynamic Casimir Effect is more than just a theoretical curiosity. It has profound implications for our understanding of the universe and potential future technologies. By manipulating the vacuum, we might one day be able to generate light and other particles on demand, leading to advancements in quantum computing, communication, and even energy production. The study of the Dynamic Casimir Effect also provides valuable insights into other areas of physics, such as black hole evaporation and the early universe. As we continue to delve deeper into the mysteries of the quantum vacuum, we can expect even more surprising and potentially revolutionary discoveries in the years to come.